Welcome, everybody. We're going to be working on Unit 6 this evening, and we're picking up where we left off from last week. If you remember, in Unit 5, we talked about the AI project cycle, and we called that Part 1. And if you remember, in that unit, basically, the project life cycle was broken down into 6 steps, and we basically covered the first 3 of them during our class last week. And this week, we get into I like to think of it, some of this is like the meat and potatoes part of it, of the project work, but the last 3 steps. Now, when you're doing the AI project cycle, and I'm going to kind of be weird about this, and I'm actually going to bring up the previous PowerPoint just for a moment, because I want to show you the graphic of the steps. Okay, there we go. That was kind of weird. Right, but I want to find that graphic, and I think, okay, this kind of shows all the steps, and we talked about problem scoping, right, and the importance in doing any project work, regardless of the modality of the project, right. We talked about the waterfall approach, right, traditional systems development life cycle, which is a cyclical pattern. We compared it to the agile approach, which is kind of like microcycles, where you kind of adjust as you go. Like sometimes you change your goals as you're moving through it. And then we started to address all these different areas. We talked about problem, data acquisition is really important because good AI is driven by good data. So you have to acquire the data somehow, and then you have to look at the data, explore the data, understand the data. And we looked at different sources for information, all those pieces. Right. So I'm just trying to like give us a solid underpinning of where we came from last week, right? So you guys aren't forgetting, like, oh yeah, he did talk about all this stuff, right? But now we get to the part where, and this is true with any of the methodologies, by the way, where more of the actual work happens that we think of as the work that we do. But here's what's really fascinating about projects, regardless of modality or methodology that you use, is a lot of times when you work on a project, there's a lot of thinking about it, thinking about what the problem is first, how feasible it is, what approach we'll take, what information do we have, what does that information look like, right? So those are like, you see how like the 3 steps here are reflected in what I just said. And then you get to the point where like, okay, now we really have to do the AI part of it, which is what happens in the modeling and the evaluation areas. This is where you're really building the AI stuff, and then you deploy it, meaning you put it out into the world and you use it, right, to do things in the real world. Like any other IT project, often the preparatory steps to get to the building of the actual stuff sometimes is more work than the building of the actual stuff. This is the weird aspect of any project. So, however, right, and one of my standard analogies, right, you want to build a house, you don't run down to Menards and buy a bunch of 2x4s, hammers and nails and get busy building. You start with figuring out how much is it going to cost, where's the land where I'm going to build the house, do I own the land, what kind of house am I building? I need a blueprint. I need an actual tangible plan, and I need to figure out the costs, and I need the money and all those things. And then you get to building the house. And when you plot it out as a project cycle, that's one little piece of the whole thing. And then afterwards, of course, you have to maintain the house, and then later on you might want to improve the house or add to the house or something, right? So you go through the cycle again. But this is where we came from last week. All right. So now, and I opened that up in a very silly way. We're going to go into the Unit 6 materials. I'm going to go into presentation mode here. That's kind of a weird little blurb that popped up there, but let's go into slideshow mode here. And yes, we are starting from the first slide, but I'm going to flip screens like I always do. And we're going to dig into the last 3 steps of that project cycle and start talking about them and understanding what some of them are. And as I was kind of mentioning before, it is as we get into these materials that we start to see what some of these things actually mean now. And we even have like mathematical formulas we're going to start looking at. So you're going to start to get like what I think about is like maybe some of the first real tangible aspects of like how does this AI stuff actually work? You know, and that's starting to come tonight, right? And I know like some of you are holding your breath going, you're never going to get there, right? But we are, right? A real important part of working with any form of data, right? And especially when it comes to AI, is to look at an aspect of it we call modeling. And when we say modeling, I want to be very clear on this. This is mathematical modeling. It's built on math. It doesn't come from thin air. You know, we don't just like train an AI based upon like what I think it should do. You know, we base it upon data, we base it upon mathematical formulas, and a model is basically a representation of some sort of a scenario mathematically. Why do we use math to do this? Because math is tangible, it is quantifiable, it is repeatable, it sets a pattern that we can follow. We use formulas to do this, and we use systems to do this. Are there new models coming out all the time? Absolutely, right? This is a young science, but some of the stuff that is the fundamental pieces of what we do, surprisingly, has been around a very, very long time. So AI work and some of the models and stuff we're going to look at, this stuff's been around for a while, and that's maybe the bigger, like, mind-blowing thing about it, I think, right? So when we start to look at AI modeling, and I want you to notice here, even in the first bullet, they're pairing AI with machine learning. Machine learning, in a way, is kind of one of the more fundamental aspects of doing AI work, because it isn't really concerned with like trying to simulate human intelligence necessarily, but it is using those mathematical models basically, in this, as it says, to replicate a decision process to enable automation and understanding, right? And we looked at like what automation is versus AI, right? But if you think of like a machine that does a repetitive task and maybe has the capability to recognize, hey, there's a part missing, right? And don't continue or don't keep building it if you know the part's missing, that kind of thing. All the models are basically mathematical algorithms, and I do want you to notice that word algorithms, because here's the overlap with programming. Algorithms are formulas or steps, you know, steps and formulas that build a solution to a problem. And if an algorithm is set up correctly, you can apply that algorithm to the situation, always get the correct solution, right? So that's what an algorithm is. It's trained using data and human expert inputs to replicate an expert's decision so that we don't have to decide every step of the way, right? We want it to be automated. The main objective is to implement algorithms, fine-tune the model, which gives the best results, right? So what is it? A system to replicate an expert's decision-making process. Right. So why is modeling important? So modeling really tries to recognize what we see in reality often, right? So for example, it says it'll help us find patterns in our data. For example, in the pictures below, what do you notice? And you notice we have one that's like kind of like a chart or a graph, looks like a scatter plot, right, folks? Right? And then we have a graphic of like, looks like a fox and her babies, right? And you notice how the fox has a box around it, and then the babies have boxes around them. So what this is telling us is that we're looking for patterns here, and we're recognizing this is a pattern that separates it from the background. So we can tell it's an animal and not like grass or brush or vegetation. And the same here, that these seem to have the same thing. How do we know? Well, there's eyes and a nose and ears, right? And the fur is a little bit different color than whatever's in the background. And so there's a pattern to recognizing something visually, right? When we look at this data set here, we notice like, okay, well, there's some patterns here as well. There's some weird K numbers, and some circles are yellow, some are red, some are purple. The purple ones are all over here, and the yellow ones are all over there, and the red ones in the middle, right? And I'm just making very base level observations here, but there are patterns, right? The purple ones are off to the right. The yellow ones are off to the left and up a little bit. right? So I'm seeing this as a pattern. I'm recognizing generally the yellow ones are over here and the purple ones are over there and the red ones in the middle. Well, there's no other red one, so I don't see a pattern with that one, but I do see a pattern with purple and I do see a pattern with yellow, right? And so how do we train machines or software to recognize these two, right? So it says the patterns are identified on the left while the foxes are on the right. They are the results from modeling the data. And how do you create a model? Right. It says the process of creating a good model occurs through training, and training is a method of fine-tuning a model to best fit our data. So in other words, your initial glance at the information might not be the most useful aspect of it. Sometimes you get your draft version of your model and then you try it and you go, does that represent what the real world is doing? Well, sort of, but not exactly. So you tweak it a little bit and you keep tweaking until the model, as closely as possible, can represent the real world data of what's actually happening. All right. So here's some use case examples, right? So they talk about email spam filtering. This is something like if you're using Gmail, for example, which we do here at Gateway, that happens automatically. I don't know if you guys get a lot of spam in your student email accounts. Maybe not because you haven't been here very long. But in my faculty account, I mean, it's at the point now where I don't get a huge amount. I think some of it is pre-filtered and never even gets to my inbox. But then I have a fair amount that does make it into my spam box. Every once in a while, I get stuff in there that shouldn't be in there. And certainly a great amount of times I get stuff in my regular inbox that should be in there, right? Strangely, though, a lot of times when you get stuff in your inbox, it's because of stuff you signed up for or volunteered information for, or said, I agree to some piece of software to share your data, and it's using it to send you spam. And often you can unsubscribe, or if you hit the little report spam button, it'll do it for you in Gmail. But they're using some sort of a thing to recognize automatically that something's spam, throwing it in your spam box so you don't have to mess with it. Often, those pieces of spam, especially if they're malicious, right? Because a common way to propagate malware, viruses, Trojans, cybersecurity attacks is to send you a piece of email and get somebody to click a link that they shouldn't be clicking. Even smart people fall in that trap, by the way. Our cyber security team here at Gateway, every once in a while, will send out a trial balloon message where it looks like change your password immediately, and the email address will be like gttc.edu or something goofy like that, just to see who clicks on it. And then if you're one of the workers that clicks on it accidentally, well, then they send you to more cybersecurity training, by the way. Whereas if you notice that it's spam and click report spam, you're off the hook, right? But the software can do this too. So software can look at links in a document that appear to be fraudulent and do the filtering. This is really kind of a weird example, but my wife and I went to a gathering yesterday, and at one point we needed to purchase some food, and they were only taking cash, but there was an ATM there. And I went up to this ATM, put in my card, typed in my PIN to get some cash, and it declined. And I'm like, what the heck's going on here? I got plenty of money in my account. And then 2 minutes later, I got a thing on my phone. Were you attempting to withdraw money from, we were not sure it was you, so we declined it. I'm like, oh my God. Thank you, I guess, credit union, but not great if you really need the money, right? But they have a system too, where apparently maybe that ATM had a skimmer on it, or maybe, who knows, right? Maybe they didn't see it as a good ATM brand, or I don't know. But thankfully, there's systems in place, so they're using those systems. Now, is the question, is that really AI, right? Or is it just some good algorithm that goes, we've had problems at this machine before, so put this one on the bad list. So if we get people, on that machine, let's not let them get money. Right. Here's another one, sentiment analysis, right? So whether the sentiment is expressed in a document is positive or negative, or an email. That's kind of a weird one. So why would this be important? Well, if you're a company that has a customer service email, you might want to filter your messages into like, hey, here's somebody saying how wonderful we are, and here's somebody saying how horrible we are, you know? And they probably have things that they scan for to figure out whether it's positive or negative. Like if somebody's saying I hate, they probably, I want my money back, or whatever their situation is. They can probably assume negativity and or positivity. So that's kind of an interesting one. Animal identification, that's kind of an easy one. There's a whole bunch of little links here too, if you guys want to see where these images came from. But that's not an unusual one, is like what we were just doing. We can look at that photograph in that previous slide, right? Like in that foxes, there's not a lot of color or contrast variation in that photograph, but yet as human beings, I can look at that photograph, even if I'm colorblind, and identify the fact that there's some sort of a mammal, probably a fox or some other, wild dog format there. And images and recognizing different animal types is a total type of a model that you can build. And so can you differentiate between one and another? Okay, so here's where modeling is kind of interesting. And okay, why modeling is important. We can look at, for example, at a series of numbers, and the point of this, by the way, is to show that data drives models. So here, let's try this activity here. It says, given the following coordinates, so they're looking at these data points right here, how can you predict the coordinate for the next set of numbers? Now I'm going to do a little annotation here, which means I'm going to draw on the screen, right? So we're looking at these 4 sets of numbers, right? I noticed that the first number in each one is climbing up by 1, right? Then I noticed that the second number, well, it starts at 2, and then it doubles. No, it doesn't double. It adds 2 each time. So this one increments by 1. This one increments by 2 as it moves forward. So it would be easy to guess that the next value, so if I was to draw it in, I would do parentheses and I would type 5, comma, what? 10, right? Because we're adding 2 to the last value. And if I carried it forward, it would be 6, 12. Yeah, horrible, but I tried. Right? There's a comma in between. But that's a pattern that we see, and we recognize it. Well, maybe some of you didn't recognize it right away, but generally speaking, like most of us that have done any coding or work like this, we kind of see these patterns, right? And this can be expressed as a mathematical formula. So I can say for every pair of numbers that I put in, or for maybe if this was my x, or what we see in calculus is often we call that the n, the number that we're putting in there. For every value of n I put in, what am I getting in this position, right? Well, we start at 2, right? And then we add 2 each time. And I try to very primitively express it here, but I could write it out as a mathematical formula for a series of pairs of numbers, right? It is mathematically explainable, right? Okay, so let me clear the drawings, and you'll see kind of like the pattern the author is doing here. All right, so I'm going to flip to the next slide. And I thought there was an in between, but there's not. All right, so the first slide wasn't that hard. Now I got a different pattern. All right, let me tell you what I'm spotting this time. All right, so I'm spotting that each pair of numbers also starts with a sequence. So, right, and so it makes sense that the next value here is a 5. But what goes here? Okay, now I'm trying to look at a pattern. I recognize the pattern. The first character in the pair is easy. What is generating the second number? All right, let's try to figure it out. Okay, they're starting at 2, not at 1. And then when it goes here to here, it goes, it's +3, right? And then if I go from here to here, it's +1.
It's a 1 and then 3. 1 and then 3.
Yeah, I mean, that's the assumption, right? Yeah.
So the next one would be 10.
Okay, so the next one would be, because we would add 1, right? But you notice, do we really know that that's the next value? Well, we really don't. But if we assume it's the next value and that the pattern continues, and that's a horrible drawing, I apologize, but it's very hard with the mouse, by the way, to draw on the screen. But this is kind of what we're trying to see. We're trying to find the pattern and establish it, and maybe that truly is the value, or maybe it's something else. And then, are you really confident that that's the next value? And by the way, I'm not giving the answer, because this is just kind of putting the information out there for you to think about. Matthew.
I think the answer to this one could also be solved with the pattern of the coordinate in that parentheses that you're about to solve for, the next one, is equal to the first coordinate in that parentheses plus the previous 2 parentheses all summed up.
Yeah, you know what?
Or no, that doesn't work. Never mind.
Now Matthew's thinking in a way that I think, right? Because that's not the pattern that I was seeing either. So, in other words, you're saying that these 2 add up to this.
Yes,
okay.
But
okay.
The first one.
Okay, so to follow that pattern, does this one add up to 6 though? The answer is no.
In my opinion, the next one is 5, 10, and the following one would be 6, 13.
Yeah, and that's what we assume, right?
That's right. That's right.
We're being assumptive here, but I love that Matthew spoke up though, because when I first looked at this myself, I didn't recognize the +1, +3 thing at first, right? And maybe that's not really even the pattern. We just don't know. I'm gonna argue that if you had more data points, I could see the pattern more clearly. So so what does it tell you? More data helps you see the pattern more clearly. We just don't know. I also did this thing too, and I was kind of thinking like Matthew was, which was like, okay, so maybe the 5 comes from adding up these 3, and then maybe the 6, oh wait, that doesn't work. I started doing like that stuff. And I like the +1, +3 approach. I think that's probably it. And I think if I put it into like Chat GPT and asked it to analyze it, they would probably say that. Right. So if somebody wants to try it. Now it says, please show your work with the calculation and the graph. They want you to graph it. I'm not going to do that, but you could graph it. Kathleen?
I think the pattern is double. So it's the 1 is double. Let's give you 1, 2.
Your voice is cutting in and out.
And then the next one will be a 5. Oh, I'm so sorry. I'm having a little bit of connectivity, so I got my camera off. I think the pattern is double. So the 1 is double, gives you the 2, and then the next one in the sequence would be double plus 1. So the 2 would be double, which makes 4 plus 1.
Then what happens here?
Is what I think the
pattern that's not a bad thought here. Okay, so like here, in this case, we're taking the 1 and doubling it. So we just say ×2, right? Here, we're taking it's ×2 plus 1. Here it's times 2 again. Here it's times 2 plus 1. But let me just ask you, is that really any different than the plus 3 plus 1? Okay, well, it really depends, because if you get to the next thing that we anticipated would be 5, 10, that would follow that pattern. This would be double. And then the following one would be 6, 13, right?
13, yeah.
Both algorithms,
double plus 1, yeah.
Magic. Both algorithms work so far. Okay, so now the way you really test it, right? And this is, I love this kind of stuff, right? And let me tell you why, right? Because this is like puzzle solving, and this is part of what this field is about, is solving puzzles, and then training software to solve the puzzles too, right? So if we follow that approach then, and 7 comes next, what's the next number? 14, and then 8.
7 and 14, but it's double.
Right, because this one's times
16 plus 1, so it'd be 8 and 17.
This one's times 2. This one's times 2 plus
it's
1.
Double.
So the pattern sticks, right? So we have, I think we've correctly analyzed the pattern. Whether you use the plus 1 plus 3 approach, that worked, right? Or the double plus 1 every other time, right? Now, how do you express this as a mathematical formula? Well, that's not as clear, right? So that's one of the reasons why stats is important and math is important in this stuff. It's also why it's important to work with actuaries and data scientists who are all about the math. But I love these kind of little puzzles. They're very, very fun, but also kind of tells you a lot about how these things work, right? And because once again, it's pattern recognition. All right. Next activity. What are the animals? Okay. So which one's a cat and which one's a dog? Now notice, as human beings, we just look at it and go, oh, that's easy. It's like dog, cat, cat, right? Easy, easy peasy. However, you have to admit, that's clearly a dog. That's clearly a cat. That's clearly a cat. But now notice how these two images, though, they're not quite so clear, right? Like, you know, one thing that differentiates a cat from a dog is, well, they tend to have pointy ears, not always, but tend to, right? They tend to have whiskers. They tend to have a certain face shape and mouth shape where I can look at it and go, cat. And the dogs do too, but if they do have whiskers, they're not as pronounced or as large. And then you have these anomalous ones, like this guy's like all wrinkly, and I can't really quite see his whole face, and he's not super fuzzy like this dog, right? But I still know it's a dog. Why? Because I recognize that as a certain breed of dog. Can't tell you what it is offhand, but I recognize it. I've seen them. You know, somebody in my neighborhood has one, I think, right? But then we also have this cat that's like partially wrapped up here. You can't see both sides of the whiskers. You can't see its torso. And once again, like this dog has like this wrinkly skin blanket thing kind of going on. And we still don't mistake it for a dog. Now, can you imagine if you're trying to train a piece of software to make this distinction? How do we train the software to recognize this is a cat and that is a dog, especially when it's wearing a party hat? I don't know if you guys picked up on that. Yeah, it's all in the details. And it's much more different if you see the whole animal, or you see the torso, if you get like a profile view versus a straight on view or whatever, right? So all of those are pertinent. So what they're trying to show us here is that the stuff that we just did, we were using certain types of models intrinsically to figure out the solutions. This is really kind of, I think, fascinating, right? So basically what we introduced to you are the concepts of regression This is where we compare two values, and classification models. And that's like looking at, a dog and a cat and being able to tell the difference. So the first two activities, right? Simplified examples of regression problems that can be solved with the help of a regression-based machine learning model. We can write formulas built upon what we did there and feed that into a machine learning model and then have it operate and calculate out those patterns as far as we want. We don't have to do it, right? And then I'll have you ponder this, like you could write the formula in Excel, data analytics people, right? And once you have the formula correct and it's set up correctly, then you can just drag it down and it does it. It's kind of the same thing, right? So once again, AI or well-written software, or well-written code. Yeah, even the code in the spreadsheet is technically code. The third activity, it says it's a simplified example of a classification problem that also truly is a machine learning model. So there are visualization or classification models that we can use as well. All right, I am going to play this video here. This does not take very long, by the way.
Hi everyone. In this video we will learn about various sub-techniques of supervised and unsupervised learning. These techniques are classification, regression and clustering. Let's begin with classification and regression. Both of them are different techniques of supervised learning, with the major difference between the two being in the kind of labeled data they deal with. If you recall, we talked about categorical and numerical data in the last video. In this video, we will understand what each of these data types mean with the help of simple examples. We will also learn which kind of problems will be better suited for either of the techniques. Imagine we have the following data for a group of students. Here the amount of time spent each day in studying and playing is shown along with the grades they receive at the end of the school year. As you can observe, the grades they receive categorizes them into different groups. Data of this kind is known as categorical data. Categorical data is qualitative in nature, meaning that it denotes a quality or a characteristic rather than a quantity. A quick way to check if your data is categorical or not is to check if the label is a number. If it's not a number, then you can call it categorical straight away. However, if it's a number, make sure to check whether any mathematical operation can be performed on it. For example, if you are dealing with a label like age groups, then you will notice if you try to add them up it does not make sense. However, if we are dealing with something like marks, addition would make sense, and hence marks are numerical in nature. When we are dealing with categorical data, then the technique of classification can be applied. As the name suggests, classification is the process of putting data into different classes or categories based on previously labeled data. Typically in classification, we often input features of labeled data. This is to identify the class of data points not originally part of the data fed into the model. For example, if we consider the previous data, a classification problem could be to predict the grade received by a student based on the inputs of hours spent playing and studying. Data dealing with numbers is called numerical data. Numerical data is quantitative in nature, meaning that it signifies a measurement or a quantity. For such kind of labeled data we use the regression technique. Let's say we have the marks obtained by a student over the years. Based on this we can predict what the student is likely to score in the coming year. This kind of technique used for predicting some quantitative value is known as regression. Now that we are clear with classification and regression, let's see what clustering is. Clustering is a kind of unsupervised learning technique where unlabeled data is grouped into clusters after training is complete. For example, if you have a set of images depicting the shadows of different forms of wildlife, then the clustering algorithm is likely to form two separate groups. One being animals and the other being birds. Notice that we talk about shadows since the data we deal with is unlabeled. Depending on the kind of data available, and the problem you are trying to solve, you can use either of these techniques. Typically, we would use classification if we have labeled categorical data and wish to identify which class a new data point would belong to. Regression is useful if we wish to predict numerical data such as prices, weather, etc. based on past labeled data. For uncovering correlations between unlabeled data points, we can use clustering. To recap, in this video we learned the major differences between the three techniques of classification, regression and clustering. We also learnt in which situation we should use either of them. Thanks for watching.
All right, that took a little time to go through, but there's a lot of really useful pieces in there, right? Terminology, understanding what classification and regression really mean, and the fact that we have different types of data. So just because something is a number doesn't mean it's necessarily numerically acted upon, right? And he used like, I like the example, right? Like, so for example, they had like an age range, you know, for people. That's a category, it's categorical information. Even though there's numbers associated with it, it just really tells you that you're in the category of being young or not so young or old or very old or whatever. Where you have actual values, like when we looked at, like in the data analytics class, the correlation between height and weight, right? As a person gets taller, they tend to weigh more. Not always, but that's a good general rule. And that's mathematical, it's predictable. So like, for example, if I notice that most people that are 6 foot tall tend to weigh 200 pounds, then it would be safe to assume that if they're 6'2", they might weigh 210 pounds. You know, that might be kind of a logical progression from that information. Classification, though, is where we're just kind of clustering things, and that's completely a different type of thing. It's not numerically acted upon. It is based on observation, right? But what made it evident that one was a group of, I don't know, animals, and the other was a group of birds? Like birds aren't animals, but there was, what I noticed is all of the animals seem to have 4 legs, maybe tails, maybe horns, but kind of had the same sort of body shape, where all the birds either had 2 legs or didn't display any legs or had wings or had beaks, but they certainly didn't have the 4 legs. And that was enough to make that distinction. Okay, so modeling has a lot of different types of algorithms. And once again, I don't want you to go into panic attack mode when you look at all this different stuff and go, oh my God, I got to memorize all this stuff. This will come later, right? But what we're looking at right now are some of the more common ones that are used to build AI models. Linear regression is one of them, right? So this is the mathematical aspect of it. And you'll notice there's deep neural networks and decision trees and all this other stuff that's listed here. And we will look at a few select ones here tonight to see how they operate and actually kind of get a little bit of an understanding about what some of these things are as a collection. As you get into machine learning, these will become tools that we use to build our models, right? So you don't just build a model just because you set up a system. And if there's already mathematical or base mathematical models that you can apply and then tweak aspects of them to generate your model, well, there you go, right? To get you like in the right area. All right, let's move on. So these are the 3 that we're going to kind of look at this evening. And we're actually going to kind of dig into them a little bit and look at how they operate, what they look like, charted, what the formulas look like. And right, and if you're math phobic, you know, hold on to your seatbelts here, because some of this math does look pretty scary, by the way. When we look at linear regression, and I love the direct correlation here, once again, that we're having tonight between our data analytics class and the material in this class. I think it's kind of very fortuitous or synchronous, synchronicity of somewhat a weird sort, right? But this is something that we were looking at, in the data analytics class, like when you take pieces of information where you're working with two pieces of data, right? So where we can plot the data on the axis of a chart, right? And what this one is says the scatter plot of distance to destination from Baltimore, Maryland versus the cost of airfare. So in other words, what they're saying is if you're in Baltimore and you're flying somewhere that's a certain distance away, what does it cost you for that flight? Okay, so it makes sense. If you fly farther, it should cost more, right? Because there's more fuel, you know, and whatever, right? And you have to find enough people in that location that want to go to that distant spot also. But then there's also the possibility that maybe one of the distant locations is somewhere, I don't know, like Las Vegas, where everybody flies to it. So there's lots of flights and maybe it doesn't cost quite so much. So maybe some of those like fall way down on the chart, and then some stuff goes the other direction because it might be an anomalous location, like flying to Milwaukee, like who wants to fly to Milwaukee? Or let's make it even weirder, Rockford, Illinois. All right, but the point is when you take all of the information and you plot it, right? So you take all the different airfare amounts and you put it on here, and this is what we call a scatter plot, by the way. So these data points are generated by an actual airfare trip and the cost of that trip. And notice that we have placed amongst the data what we call a trend line, and that trend line has a slope to it. And this is what we call a linear regression, meaning if I look at this as an algebraic formula, which they have posted on the screen here, this is the formula. So 0.117x plus 83 point whatever is the formula. So for any given value of x, I can predict it'll probably be along that line somewhere. So even though this data does not seem tightly correlated, it generally has a shape that follows that line. It might stray from that line. It might be right on the line, but generally it's somewhere within the range of that line. And then you get this weird thing, and you might be learning about this in your stats class right now, if you're taking stats, is that the R2 or the squared value here, this is basically showing us what the deviation is that's normal from that line. Yeah, so there's like a range of like variability that's kind of normal, right? And most data points will fit in there. I wouldn't say this is a supremely correlated set of data, but it is relatively correlated. And the fact that somebody could plot a trend line shows some sort of a correlation, whether or not the data fits it, right? So this is a very common tool to use. Linear regression is one that's used all the time to make predictions, but we are only working with two pieces of data here, right? So this is an important thing. In the data analytics class, we started talking about, you know, like when we start adding a third piece of information, how do we show that? You know, that gets a little more challenging. All right, there's this other approach, and this is one that's very common in modeling called the K nearest neighbors approach. And what it does is it says it predicts the class of the object we want to find based on the surrounding objects, right? It assumes that similar objects are located nearby. And this is really weird, but it says usually the number of neighbors are odd numbers to prevent a tie. So in other words, usually you want to put an odd number of information on the screen, right? Then we also have this, like, what's this thing in the middle, right? Remember we had that red dot on that one chart? But okay, so here they're showing some blue squares. They're kind of all over here, and then we have some red ones. Some are over here. But would it be safe to assume, for example, that maybe this piece of information really belongs with the red ones? We're not really sure, right? Because this is a very generic image. But generally speaking, the data is grouped together. So there's the assumption is similar things are grouped together in space, basically. All right. Another one that's kind of interesting, we will watch this video here in just a second, is this one called support vector machine. So let's watch the video. I am going to record this in, and hopefully YouTube doesn't flag me for putting another YouTube video on here, but If it does, then I'll have to cut it out, but we'll deal with that in the aftermath.
Brad Schimmel would be one of the most extreme justices in Wisconsin's history.
Sorry for the ad, folks.
In machine learning, one of the most fundamental tasks is when you have a bunch of objects that you want to classify into two categories or more. Is this picture of a dog or a cat? Is this dog going up or down? SVMs, or support vector machines, are some of the simplest and arguably the most elegant methods for classification. Each object you want to classify is represented as a point in an n-dimensional space, and the coordinates of this point are usually called features. SVMs perform the classification task by drawing a hyperplane, that is, a line in 2D or a plane in 3D, in such a way that all points of one category are on one side of the hyperplane and all points of the other category are on the other side. And while there could be multiple such hyperplanes, SVM tries to find the one that best separates the two categories, in the sense that it maximizes the distance to points in either category. This distance is called the margin, and the points that fall exactly on the margin are called the supporting vectors. To find this hyperplane in the first place, SVM requires a training set, or a set of points that are already labeled with the correct category. This is why SVM is said to be a supervised learning algorithm. In the background, SVM solves a convex optimization problem that maximizes this margin, and where the constraints say that points of each category should be on the correct side of the hyperplane. In practice, you don't have to worry about the implementation details of this optimization problem. Using SVM can be as simple as loading a Python library, preparing your training data, feeding it to the fit function, and calling predict to assign the correct category to a new object. The biggest pros of SVMs is that they are easy to understand, implement, use, and interpret. Furthermore, they are effective when the size of the training data is small. The simplicity of SVMs can also be a problem. In many applications, the points cannot be separated by a hyperplane. A common workaround in this case is to A. Augment the data with some nonlinear features that are computed from the existing ones, B. Find a separating hyperplane in this higher dimensional space, and C. Project back to the original space. A clever technique known as the kernel trick allows us to perform all of these steps in a very efficient manner. And now that you know about SVMs, you can use them for face detection, spam filtering, and text recognition. This was SVM in about 2 minutes. Like and subscribe if you like the video, and see you next time.
Okay, and by the way, I think that's a very nicely done video in terms of efficiency. Once again, you'll notice they jump into formulas which feel very intense, and what I want to assure you is, like, linear formulas really aren't intense. Those are basic algebra formulas. They had to, in that one weird data set where all the pink ones were in the middle, they had to convert it to a 3D model and then rotate the model in a way where they could find a plane that would separate out the data sets. So, and that's just one approach, right? That's using a plane to separate the data sets. And as you can imagine, you can use much more complex shapes to do it. As long as it can be mathematically described, then it can be used as a model to do the classifications. And I think this is really kind of fascinating. Let's move on to the next slide. We are going to be taking a break here. In fact, why don't we do it right now? I think this is a great spot to do it. We're going to take a 5-minute break, and then when we come back, we'll dig into the rest of these slides. All right, folks, I'll see you in 5. Pause the video. Welcome back, everybody. We're going to continue on after our break here. And they put this little blurb on the slide that, all those other algorithms or models they were talking about, you can read up on those in your free time. I'm sure you guys will rush right out and do that. There's no rush to do it, actually. You should just wait till we present them in class. There's kind of some interesting aspects of this too, right? Because we can also kind of use some of this stuff for generative AI models and how they compare with what we call discriminative AI classification models. And I want you to understand that there's a difference between the two. And they have this little table here that starts to explain what some of the differences are, like how typical, or let's call it standard AI operates versus how generative AI operates. So, for example, in learning, right, a regular AI model looks at a relationship between features and labels, right, where the Gen AI looks at a distribution of those things. That regular AI models can classify data, but Gen AI classifies and generates new data. So it's got the ability to sort of train itself, right? The complexity of a regular AI model is less complex than the more complex Gen AI models. Less powerful. Gen AI is much more powerful, right? And this is why it scares people, actually. And using it in applications, basically, we use those types of models to do our classification. But with Gen AI, we have data augmentation, semi-supervised learning, and unsupervised learning, and that is where it trains itself, right? That's kind of weird, too. But that's how, like, humans operate, right? We train ourselves often, right? Even when you go to school, right? The work is still yours. And some of the examples, of course, like what we just looked at, like regression and vector machines and decision trees, and some of those classic math models fit into the regular approach, where the Gen AI uses what we call generative adversarial networks. We talked about that briefly. I don't know if you guys even recall it. And then variational autoencoders, both were brushed upon briefly. So in other words, they have a different approach for kind of moving forward. So let's talk about those kind of weird approaches. So what we call GANs basically are used to create, things like realistic images and translates images from one style to another, create text, right? So the generative part is to learn a generative model, right? So this is how it operates, which describes how the data is generated in terms of a probabilistic model. The adversarial part is the training of the model done in an adversarial setting. And that sounds like you're going to have like an argument with it, but really you have to train it on what good data is, bad data is, by usually having examples of good data, right? And also examples of bad data. And then networks, right? They use deep neural networks. So in other words, they use machine learning algorithms to train themselves, right? So it doesn't come from anywhere. So that's why like the fundamental AI stuff is important, even with the generative AI stuff. So they give this example, right? And we sort of kind of tinkered with this tool a little bit, DALL-E, and this is DALL-E 2. So it can make images from texts. For example, if you typed in a photorealistic painting of a cat riding a unicycle, it would generate an image of a cat riding a unicycle that looked like a photograph as opposed to like a cartoon image of it, right? Here's one where the prompt was a photo of an astronaut riding a horse, right? And it kind of looks like that. And it's kind of weird that it's open space, but here once again, we're talking about these classification models. We move on to the other type. So the variational autoencoders, or VAEs, and they generate new stuff by encoding data points into a latent space and decoding them back into the original space. So in other words, they kind of build it virtually first, and then they present it to you, right? So sometimes when you ask a Gen AI model to create something, it thinks on it for a little bit. It doesn't like spit out an answer. That's what a search engine would do, right? And I don't know how much you guys have experimented with Gen AI, but I did some interesting stuff earlier in the week where I was taking a data set from a spreadsheet and dropping it in and asking the AI some questions about my data set to see what it would say. Right? Here's something you should know about the free versions of ChatGPT and other tools, is sometimes they have limits. So I did so much of that in experimentation that it cut me off for 24 hours. I said, okay, that's enough data processing for today. You can come back tomorrow and try this. 24 hours, you gotta wait. And I don't know if anybody's ever encountered that. And the reason for that is it was doing part of what I'm talking about here, right? It was reading in my stuff, analyzing it, looking at how it was set up, what's wrong with it, what's good with it, whatever. And then it would try to detect what's wrong and then give me a result back. So it's a little bit different approach. These can be used to generate images, music, and text. Right? And I think it's really interesting that, it can create that kind of stuff, by the way. The example they have here, if we ask Video GPT to create a video explaining the process of photosynthesis, you would simply provide a text description of the process, and then it would generate the video that shows the process step by step. That's kind of bizarre, right? We had one person in our construction sciences department here at Gateway put together a video with AI that explains all the stuff they teach in their program, complete with like simulated AI characters and kind of showing all the different processes that they do. And he like wowed everybody with the video. And everybody's like, how'd you do that? He said, AI. So it was kind of amusing, kind of see people using it for some practical purposes. But a lot of us don't even think that we can do that. But there are tools out there that help you do that stuff. But it does take a lot of what we call prompt engineering to build the right prompt, sometimes in a series, to get the output that you want. All right. So let's go back to the whole data thing, right? So let's keep in mind here that all AI is based on data. It says it would help if you had a lot of data to train your model, right? However, if you have a lot of data, you don't want to use all of it for training. This is kind of the point of the slide. You basically say, okay, we're going to use most of this. And notice the rule of thumb is 70 to 80% of the data will be used to train the model. And then we hold a little bit in reserve to test the model in the after. Because if you burn all your data on the training, then you have no data, right, to test it with. So you use a good majority of the data. So that's kind of like a 2/3 rule, sort of, right? Maybe, or 3/4 even, to train your model, and the other quarter or third or whatever to test it, right? And it says keep data distinct. Training data is only used for creating an AI model. Testing data is only used to check if it meets the benchmark requirements. So that kind of tells you like some of the engineering that goes on behind the scenes. So it's not like we can take all the data we have and throw it in there and let's train this thing. It's a majority of the data, right? How do you know if a model is working correctly? Well, now we're moving into the evaluation stage. So all that was modeling, right? So here's what we will talk about here. So, what are the evaluation methods part of it? And this is where we actually get into doing some math with it. And it says, what is evaluation? It's basically to judge or calculate the quality, importance, or value of something. Okay. Now, I want you to look very carefully at some of the words here. It's to judge partially. That is not necessarily quantifiable, right? Or to calculate, that is completely quantifiable. So you notice, right, that we're looking at like categorical data and actual numerical data, like they were saying in that video. But also when we're calculating, even though we're putting numbers on it, we're looking at things like quality, importance, or value. Like what's important to me might not be important to you, or it might not be as important to you, where something else might be more important, right? And there's a you have to judge that. You may have to make a judgment call, like who's making that decision, right? So that's got to be part of the models. It says the main objective is to evaluate on different models and choose the best model. So sometimes you have choices between models that you can use. Sometimes you use various models, together. So this is where it gets even weirder, right? So there's different types of models you can use depending on what you're trying to do, right? So in general, if it's classification, we're trying to make sure that we're accurately classifying. That's a dog, that's a cat. And then you also have this thing called the confusion matrix, right? And we'll get into what that means ultimately, but it's another tool that we use basically so that we can eliminate bad information or bad classification, right? And notice like when we had those pictures of like the cat and the blanket and the dog where we couldn't see its face and it was a really wrinkly, anomalous looking kind of dog, that we as humans very quickly can pick up on the fact that it's a dog, but the AI would have to be trained. So that's part of the confusion matrix kind of thing. So The other approach is if you're doing metrics, meaning there it is quantifiable, we can apply math to it, and then we have actual formulas and algorithms that we use. So for example, the one is the root mean square error. We'll look at that. It's a standard part of statistics, by the way, and the mean absolute error. And I don't expect that you memorize this stuff at this point, but you, over time, and I'm just telling you this, right, like as the years go by and you've worked with this stuff for a while, you will start to recognize some of these formulas. They're pretty standardly built on statistical analysis that's existed for a long time. All right, so let's move forward here. All right, so it says let's start by looking at the metrics that matter for classification. All right, so classifying, like once again, like finding the dog and the cat, right? They have the confusion matrix, so you can kind of rule out the inaccurate stuff, like what stuff might confuse you. How accurate it is, how precise it is, the recall, the specificity, the F1 score, and the receiver operating curve. And guess what? We're going to go into all of these and talk about them with some examples now. All right, so let's use this as an example. You've got a bag filled with 10 balls. The color for the balls are random, right? But as you can tell, they're red, green, blue from the chart. You want to guess whether the ball that you pick is red or not. So it's a kind of like a true false, right? So in other words, you're gonna pick a ball, guess the color, and put it aside. Finally, you tabulate your findings in the table on the right. So in other words, you grab one, you predict what color it's going to be, and remember, our goal is to pick whether it's red or not. And so we're guessing. We're not seeing this column. We're just grabbing a ball, not looking. I'm saying that one, yeah, that one's red. That one's not red, right? And we just made a chart. So it's kind of safe to assume, like, as you can tell here, there's 10 tries. The person made 6 guesses for red and 4 guesses for not red, right? And then when we look back at the actual color that was picked, we kept track of that, and it turned out it was blue. So first one's wrong, second one was correct, third one was incorrect, fourth one was incorrect, 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 correct, correct. Okay, now we don't know how many balls are in there, how many different colors. We don't have any of that information, but we're making assumptions about the classification. So part of it is to make this like weird prediction on whether or not we're guessing correctly or not. Okay. Next, we have the confusion matrix. All right. So this is where we take and we start applying some terms here. So we create this little table of 2 rows, right? What we predicted, whether we were correct or not, yes or no, and then what actually came out, whether it was red or not, right? And so we come up with these 4 different categories here. We get a true positive, where what we predicted actually was red, and we guessed it correctly. And then we have the one where it was red, but we guessed it wasn't going to be. That's the true negative. And then we have the false positive, right? Where it wasn't red, but we guessed it would be. And then we have the false negative, which we guessed the wrong thing and it was the wrong thing. Right. So we fall into this, right. The ultimate choice is yes or no, right? So there's only 2 columns for each of this. But if it was much more data, you would add more columns, right? So you can have a really large confusion matrix, but generally we're looking for true falses, but true positive, true negative, false positive, and false negative in these categories, right? So this is a really helpful slide, by the way. All right. Then we can do this little exercise, right? So for example, here it says, can you see how many true positives, true negatives, and I think this should be edited actually and say false positive, false negative. And then, so basically how many of each of these we got based upon this table. So like what you would do is if you predicted it correctly and it was what you predicted, where were we correct? Right. So then you would just basically go like, well, for number 2, I guessed red and it was red. That's one true positive, right? And then I'm also seeing these down here. They're very easy to spot. So that's 3. So I'm counting 3 2 negatives. Now the question becomes this, true positives. Is that all of them? Okay, according to this table, yes. So here's what I'm going to do. Once again, I'm going to annotate. I lost my little toolbar. So I'm just going to write 3 here. Okay, then I predicted the ones that weren't going to be it, but then it turned out to be it. So for example, here I predicted it wasn't going to be red, but it did turn out to be red. Wasn't going to be red, and it turned out to be red. And so I'm counting 2 of those. You guys agree? I'm just trying to show you how the confusion matrix works. It's confusing you. Right. All right. Then we go to the false positive, and this one. Okay, so the table works like that: false positive, false negative, whatever. So we look at this one where we predict it to be red, but it wasn't. We predict it to be red, and it wasn't. So here's 1, 2, 3. So I got 3 here. And then we predicted it not to be, and it wasn't, right? So we picked non-red. Here's 1, and here's 1. So I count 2 here. Okay. How many times did we do this? 10 times. All these numbers need to add up to 10, right? 3 plus 3 is 6, but 2 is 8, plus 2 is 10. Okay, so we're good. We got all the situations are covered. All right. So I'm gonna forward to the next slide here. I'm gonna leave my drawings on the screen. I don't know if the tables will overlap. We'll find out. Okay, so there's the actual value. So we did well. We guessed correctly on all of them. And it wasn't a guess, okay, folks. It wasn't a guess. We looked at the information, right? We made predictions. Either our predictions are right or wrong, or sort of right, sort of wrong. I mean, I don't know how to like really explain those any better, but these are the possibilities. So this is the confusion matrix. And then you notice that based upon our predictions, what happened to be true, right? So this is kind of like one of the fundamental aspects of kind of working with these confusion matrices, by the way. So this does convert to mathematical formulas. Okay, so I know that people, like, once again, I always say, people kind of freak out to the math, but let's just look at this in conception, right? We're not crunching numbers here. But basically, what we're looking for is a measure of accuracy where the number of correct predictions as a ratio or a percentage, basically, to the total number of predictions. So we made 10 predictions. How many of them were accurate? Okay, so if you go back, how many of them were accurate? Well, what would be accurate? This is accurate. Well, the 3 reds are all accurate, but also where we chose non-red and it was not red. So I'm counting half of them were accurate. That seem right? Yeah, that's just like kind of just doing it mechanically like that. So basically what they're doing here is they're showing you the math. You basically take the ones that you guessed correctly, so true positive and true negatives, and then taking all the other ones, so all 10 of them, and then you come up with your ratio. And so these were the numbers that we had. This is it converted to math. I counted 5, right? And then we put that over 10, that comes up. So our accuracy was 50%. So we were 50-50 on guessing, right? So that's a confusion matrix and how it operates, right? The next thing we look at also is the precision. So this is another aspect that we're measuring, and this is a different measure, and it says it refers to the fraction of accurate positive predictions out of all positive predictions. So accurate positive predictions out of all positive predictions. So in other words, chose red, and it was red. All right. So referring to our examples, what would be the precision? The number of correct positive predictions, total positive predictions. So we're eliminating all the negativity out of here. So in other words, the ones that the three where we guessed red right exactly versus all the ones that we got right, even when we were guessing that it wasn't going to be red. That's what we're measuring here. So that's a total of 6. Once again, we end up at 50%. So our precision was 50%, our accuracy was 50% with this measure as well. There's another aspect of the data we call recall. Now, recall says it's a fraction of accurate positive predictions out of all actual positive. And notice what measures we're looking at here. So the correct positives, red, right? With red and a false negative, meaning the ones that were incorrect in the other direction. So putting the numbers in here, once again, here we got a little bit higher number. Here we're scoring 60%. So recall measures out to 60%. There's also the measure of specificity, right? Refers, now notice we're focusing on the negative here in the top part of the equation. So the fraction of accurate negative predictions out of all actual negative. So in other words, all the ones we got wrong compared to all the ones that were completely wrong. That's how I would quantify that. Once again, we know what those numbers are now because we keep seeing them. That was only 40%. All right, moving on. There's also this thing that we call an F1 score, and I want you, this was a little bit different kind of formula here. There's multiplication in this one. So this one considers both precision and recall. So we're taking the numbers that we calculated from the others, so precision times recall, multiplying it by 2, and then adding precision and recall in the bottom. So take a look at what this does. Once again, referring to our numbers, right? Now, precision and recall were calculated, right? So if you want to know what precision is, you would go back a couple of slides and look at that formula. So you can insert that whole formula here in this spot. Same for recall, same for that, and same for that. Right? These numbers aren't really complicated, but what they're showing is we're taking the 50% times the 60%, multiplying it by 2. Then we add together the 50 and the 60% down here. We come up with a 1.1 in the divisor and a 0.6 up top, which works out to an F1 score of 0.55. I'm just showing you guys how the math works here. Then we also have what the data looks like as we plot it, right? So for example, if we are randomly kind of selecting the data, we get this line, assuming kind of like a 50-50, right? So in other words, anybody could get this, with over time and a random number of attempts, it's going to be, that's what you're going to get. Just randomly, that's the value what you're going to get. If you've set up your classification so it works really, really well and can identify things knowingly, you would push the lines or the charts here all the way up to the corner where 100% of the time you're classifying it correctly. And often this is not completely attainable, right? Not even for human beings. Have you guys ever done one of those CAPTCHA things where it says identify all the pictures of a train, right? And there's 9 little things and you click on them. And oh darn, there was one in that thing. It was just really kind of, messed up. Even humans can mess up on classification. But the goal is basically to push these curves or the receiver operating curve up towards that higher level, towards the perfect classifier. So at least you're getting most of it correct. That's kind of really the goal. So it says the objective is to get a curve near the top left. Those formulas can be calculated with these two true positive rates and false positive rates, right? And we don't want to be down here, right? We want our true positive rates to come up, or upper left side there. Right. Now we're going to look at some of the metrics that we use for regression. And this is, we start like once again throwing in numerical calculations now. So now we're not like guessing if a ball is a certain color. Now we're going to use math to do the work. Okay, so let's take a look at the first approach here. So they have a little table here where it says you're monitoring the price of the stock market, right? So then you keep checking the price of, let's say, one stock, and you're looking at its price. And every time you check, here is the listing of the actual price of the stock. And if you look at the numbers carefully, it goes up, it goes down, goes up, it goes down, right? It changes. But you are trying to make a prediction of what it's going to do, right? And there's people that do this all the time, right? That, like, in some cases, like people who professionally trade stocks, or sometimes brokers will do it on your behalf, will have, like, they think they're in the know and they know what's going to happen, but often they're just guessing, or maybe they have algorithms. And from what I understand now, a lot of stock houses are starting to use AI to do some of these predictions. It's just kind of fascinating. But here are the predictions that were made as opposed to the actuals. And notice that, there's kind of some recognition here that's going to go up and down. But generally what they were shooting for overall is that it would go up, right? By the last metric, it went up. Now, if you look at the actual price, in the long run, it did go up, but it didn't go up quite as far, right? So you make these predictions, basically. Now, all right, here's like where you start seeing these formulas and going, yikes, right? And what we're seeing here, this is the formula for calculating the root mean square error. And it looks a lot scarier than it is, because first of all, it's written in calculus notation. And calculus notation is really not that much different than, writing a formula in programming where we utilize a loop or a range of values. That's really what some of these generic terms mean. So, like, without having you guys go and take a calculus class right now, so where you learn this terminology, I just want to explain to you that the big capital letter sigma, which is the S from the Greek alphabet, the capital letter version of it, implies a sum. Right? So the sum of all the values generated by the formula. Then you also have these little sub numbers here, right? Meaning that we will start our values counting at 1 for the sub numbers. And notice what we have here, y is indicative of one of the values that we're throwing in, minus what the actual value subtracted by the assumed value. That symbol there is our estimated value, I think is the correct way to say it. So you take the difference of what you're estimating and what it is, and you're squaring it. Why do you square it? Well, sometimes you subtract a number from 1 and you end up with a negative number. But if your estimate is, larger than the actual, you might get the opposite, right? So you might have a negative number or a positive number. Squaring it gets rid of the negative symbol, and it just gives us the distance. And then that also explains why we have a square root around the whole thing. So we square it to get rid of the negative, and then we take the square root to get the real number again. Okay, that's kind of the mechanics of it. Ultimately, the equation that we're working with are for values of n, where n is in the denominator. And we kind of go into this whole thing. And like, again, I don't want to teach you calculus right now, but I just want to teach you there is a formula that you have for this. And when you use pre-configured AI libraries or machine learning algorithms, and you understand what the formula does, that's actually enough. You don't have to know how to engineer the formula or write a mathematical proof for it, right? You're just utilizing it. Okay, so, but I am showing you the math because it's in our slides here. So what they're saying now is, now if you take that information we were just looking at and you start applying these mechanisms to it, this is where we start to get some of the results. So for example, we pump stuff into the formula, right? And what we're looking for, and ultimately this is what we're, the squared difference from the actual. So we're taking the difference between the two and we're squaring that number. Okay, what's the difference between these? It's 0.1. We square it. What's 0.1 squared? 0.1. 0.01. Okay. And same here. So same value.
Can I make a comment?
Yes, George.
I think that y hat is the mean. They're in the root mean square error formula. They're not doing it from each one. They're doing it from the mean.
Okay.
Is that correct?
They're doing, well, the mean, okay, so the mean is actually calculated separately, right? So in other words, that's where the n comes in here. These are the number of observations, right?
Yeah.
And right now, like this piece here that we're seeing in the column is the result of this part of the equation, right?
Oh,
Observed, actual, and square. So these are calculated here.
oh, you're right. Yeah, you're right. I thought the hat meant mean though. Sorry, I'll be quiet. Okay, thanks.
I think in this symbolism, it means actual versus estimated, right? Like you like models telling you you're going to follow this trend, but what you actually observed at this point was a little different, and then that allows you to basically, square those differences, add them all together, take their average, and then you get this, the conglomerated sum of all those weirdnesses, right? And it comes out to this weird number, which is 0.25. Now there is a follow-up to this here. So, all right, and of course I was hoping they were going to plot it, but basically what it shows is the root mean square error is that we can vary by 0.25 on average. So generally speaking, whatever your prediction is versus the actual, chances are you're off by a quarter number. Now, because the price is here, let's say this is $2.10. What this is telling us is that on average will be plus or minus 25 cents on our guess. That's what that's telling us. That would be the normal range of variance. All right, so let's move on to the next one because we are quickly running out of time. This one kind of does a similar type of activity, right? And notice how this one doesn't have square roots and squaring. They use a different approach, but it's essentially the same formula. We still have the same n values and j values. We're still looking at the actual and the difference between the predicted and the actual. But these two symbols here in mathematics represent what we call absolute value, meaning that we don't have to square it, it just negates the negative number. It's kind of the same thing. I don't know if you guys are feeling where I'm going with that. The objective, of course, is to make the value of what this generates as small as possible. So we put in the same data, use a slightly different formula here, and then you notice that this one gives us a variance that's a little bit tighter, right? So this is a tighter model to the data than the previous one. So this number is better than the previous number that we looked at because the variance is smaller. Okay, moving on. Now, as it says here, so now you looked at some of the metrics for regression and classifications. We'll learn about some metrics about generative AI models. And this is kind of different because what we'll look at here is a series of metrics that I find very fascinating. So I want you, these are very curious. I was also strangely in a Gateway sponsored AI pilot group meeting where we're talking about what AI policies we need to have for students on campus. And I happened to be kind of like brushing up on these slides for tonight, and it matched up with what we were talking about in our session, which was really weird. Like, how do you figure out which Gen AI models are good, right? Like if you use Gen AI, how do you know what is generating is acceptable? You just take it on faith? It might not be right. Maybe your prompt wasn't good, right? All right, so they have different scoring mechanisms is what they're about to show you here. One is what we call the inception score. So for this one compares created images to reference images. So for example, if I ask it to create a photograph of a cat riding a unicycle, I can look at it as a human being and make, oh yeah, that's kind of what that is, right? And then we can judge its quality. And if you guys have tried it with different engines, sometimes your first prompt isn't very good. You got to be very specific. But if you use the same prompts on different AI engines, you will see that different ones use or have different levels of quality output, right? They're not going to be creating the same image if they're generating it from scratch. So some tools that we use to assess AI model quality, and these are often labeled by the people that develop them, right? So Frechet and Wasserstein, I'm not sure how you say it. So the first one assesses picture quality, right? Comparing the feature distributions of generated and reference pictures. So like if you ask it to create a cat, then you have a reference picture of a cat, does it look like one, you know? And so it says generated images with the lower FID resemble reference images more. Okay. The other one compares the distributions of generated and reference images just like the other, but it is more resistant to outliers than the inception score. So in other words, if we have an anomalous cat wrapped in a blanket, right, it will deal with that a lot better than the other one will, right? So we might call that outlier data. This is a kind of interesting metric here. So evaluating subjective and hallucinated content generated by Gen AI models. And if you've ever done that, asked an AI engine to create an image of like some like fantasy make-believe world, and what it creates is based upon what it knows, right? So like, how do we judge that? One is just human perception, right? So it says we use subjective quality and visual appeal. And then basically we study humans and see how they react to what it generated. Was that like, what do you think? Was that good? You know, it's based that, you know, so basically we're looking at human beings going, yeah, that was good. Or that wasn't so good. Right, that's one. The other is just by basically looking at it, and it says the quality, the detail, the conformance to specification, like did you tell it to be blue and it was green or whatever, right? But it once again, this is like an actual human being kind of looking at it and rating it, right? That's one way that we do it. And it's an important way, right? Because ultimately we're probably better judges because our brains think a lot faster than software does. Right. Another thing is that we can do comparative analysis. So like in other words, right, if we're looking at stuff that AI is creating, we can look at the reference materials once again, and this is why you don't use all of your data to train the model. Sometimes that becomes reference material for model training. And it says evaluators can assess how well the generative AI model collects training data and generates new instances with desired traits. So like, you know, how they're assessing that, often it can be manual, right? Like if you're noticing that your model's always, like you ask for a cat and it's always making it look sort of dog-like or whatever, you know you got a problem, right? And then sometimes it really depends on what specific thing you're doing. And it says how well created material meets task requirements, such as accurate and descriptive captions or a faithful style transfer, for example. let's move on here. All right, so we went through those two stages. We have one more stage to go through here, and this is where we actually deploy the stuff that we built and actually use it, right? So like we're done training, we're done building models, we're done classifying all that stuff. Our models trained, and now we're putting it out into the wild, as they say in software, or into production mode, right? So, you know, deploy, you know, when it comes to IT, you know, if you want to use like the example of like Python coding, like because all of you have had Python or are currently taking it, it's when you build the application, you know it works correctly, it's ready to be used for real, right? This is ready. Let's use it. Let's put it out there, right? So putting your work out there in IT, like how do you do that? You know, that this is kind of a weird question, right? One thing that's a lot of people don't know about this area is right now when we use generative AI in particular, we're using things that we access through cloud-based computing. And why is that? Because most of us don't have the computing power at home to run the models locally on our equipment and have it do the same stuff. However, and this is something you guys should be aware of, it is entirely feasible to do that. So if you have a computing horsepower at home, like you have like a high-powered server or a pool of high-powered equipment, often takes more than one computer to do it, and you install the large language models, the same engines that big AI companies use, and you can install it on your machine, you can run a local instance of generative AI. It doesn't have to go out to the internet. It can be right in your home. Weird, right? All right. Not normal though, but there are those people that do it. I'm just putting it out there. Right? All right. So how do you really deploy stuff? Well, you know, for most of us and in most computer and internet usage, by and large, is on mobile devices. How many of you, right? So you can do a show of hands if you wish. How many of you are running some sort of Gen AI tool on your mobile phone, whether iPhone or Android? Few. Okay. Yep. On my mobile phone, I'm running Gemini, right? Which is because I'm on Android, right? And it's easy to add in there, and that's the only one I typically use on my phone. On my computer, I use Many, right? I don't have Copilot installed in Windows. I prefer not to have that present. We had to talk about this during our session today too. Some people are like, I don't know, should I turn on Copilot in Windows? And I'm like, that's up to you. You know, my personal choice is no, I'll just go to the browser and do my AI stuff. But what would be the difference if you're running an AI engine on your local machine? Think about this. Well, if it's on your local machine and it's logged into your system like you are, it then has access to your documents, your photographs, your emails, your applications, your logins, et cetera, et cetera, et cetera. And then you can actually task it to do stuff on your computer as opposed to just generating a silly picture of a cat. Now, the flip side is, what happens to my information? And that's where I kind of draw the line. Like, I'm not sure, so I'm not going to experiment with that. I'll just use the cloud-based stuff. And this is a conversation you have to have with yourself. So for a lot of us, what we do is we'll run AI stuff through a mobile app or add on to our phone, or we go to a website like I've done in class, right? You just go to ChatGPT or Copilot and type in your prompt and get an answer, right? But the reality is when you're actually really deploying it, where most of those engines reside, do you think your phone is powerful enough to run the AI engine? Or is it really talking to something that's operating on a cloud server somewhere? And that's really where the stuff operates. Because where do we have enough computing power to really deploy AI with really, really large data sets and language models and self-learning algorithms and all these things, right? That's where we have that computing power. And that's exactly why when I was running my little data analysis on ChatGPT, it was like, all right, you had your ration of data processing for the day, come back tomorrow or subscribe, right? I finally, it was kind of interesting because I finally hit a functional limit on it, right? So I thought that was kind of fascinating. So, and here's the why: those cloud-based models that are out there, the time they spend operating on those cloud servers costs the owners of those companies money. It's a cost. So obviously my data processing was a heavier lift than asking for a picture of a cat or write my Python program for me, please. Thank you. Which a lot of people do, and I get it. All right. So considerations for deployment. How do you really deploy? Like, what kind of hardware do you need? What kind of cameras do you need? And Charles, I see you have a question, sir.
Can you hear me? Oh, sorry.
Yep.
I just want to make sure I wasn't muted. Well, it wasn't so much a question as a comment, but I clicked it kind of slowly. So I just, when you were talking about the on-device thing, like Apple's latest phones that came out, I guess like 6 months ago now, one of their big selling points was that all the Siri or whatever was done on the device, but they sold it as like a privacy thing, like it's not being sent anywhere. But also, like the other thing that's interesting is they actually haven't turned it on yet because I think they're still wanting to make sure that it works decently. So yeah, I guess it shows both things because that was their big selling point. But I know they haven't actually sent it to enabled it for anybody yet. So maybe it is harder than they thought.
Well, part of the modern architecture of the Apple ecosystem. So if you guys follow, like how their devices are developed, several years ago now, the Macintosh or the Apple people came out with their own CPUs or central processing units for computers. Prior to that, they were using chips built by Motorola in the old days. And then they switched over to Intel chips for a while, the same as PCs use. And then they came out with what they call Apple Silicon or the M series chips, like M1, M2, M3, M4 now. And what's unique about those M chips, even in mobile phones, is their architecture. So for example, on most low-level M1 and M2 machines, there's usually 8 GPU cores for graphics, 8 CPU cores for regular processing, and then they have 12, mind you, machine learning cores on the chip as well. For how many is that total? That's a lot of CPUs, like 28 CPU cores or something like that. And what's astounding are the machine learning cores. They have, in principle, if you get an M-powered device from Apple, you have a large number of processing units there that, in principle, could do that kind of data processing, right? Which I think is fascinating. So, yeah, and you know what? They are being cautious about it. They're not just like, hey, we need to do an AI thing. Let's do it really fast. And, they're being really careful about it. And I think rightly so. All right. So here's some questions you might want to ask, right? And so these are considerations for deployment. You can read these all yourself, but if you are running it on a device, does your device have the horsepower, right? Do you have the capabilities that you need to do the kind of processing that you're looking for? So for example, they're using the example of do you need to do real-time image processing, like watching the robot build the part correctly? And what does it take for it to capture the video, process the video, analyze the video, and then go, oh, the machine's messing up, hit stop? That's a lot of processing. It really is, right? So you have to have the infrastructure in place to do it. And then they also talk about how a lot of stuff now is, especially our data feeds, are done with little IoT devices, which aren't necessarily super powerful individually, but collectively they might be. But they're really good at collecting data, and then what do you do with all the data you're collecting that you're processing? These are heavy lifts, so like the one example, I always talk about the autonomous vehicle program that Racine was doing, the Badger, and how it would go on a 3-minute trip around our downtown campus, and it would generate like 100 megs of data in a 3-minute trip. That's all text. That's like hundreds of thousands of lines of text for a 3-minute trip. What if it was driving all day? Right? And what if it was a larger bus? And it went farther. These are weird things to think about. So we have to have all that infrastructure ready. And in many ways, we're just starting to get to the point of that, which is why we're seeing a little bit of a building craze going on with data centers, right? Because we need those data centers to really crunch the numbers on it. Our home computers typically are not going to be enough to do it. You do have to look at your computer resources, lots of computation and memory, enough processing power. We were talking about this. And then when you're deploying AI models, will the application or user base the scale model? So in other words, if you're loading it on your machine and then the model gets improved, do you get the upgrade? Or if it's in the cloud, it's upgraded all the time. You don't even see that stuff. But generally speaking, why people operate in the cloud, and this is unbeknownst to a lot of people who use computing stuff in the cloud, that and the one example I usually give is like a website example, but like I always tell my web students, like the NFL has a website that runs, it's probably a cloud-based website, and then most of the year, like when in the off season, like we're in the off season now, a lot of people aren't going to the website. When the season kicks in, and then all of a sudden they need more resources. The beauty of cloud computing is cloud computing resources can be controlled through a control panel. So like a lot of people go through platforms like AWS or Microsoft Azure. And as the demand for your product increases and you need more computing power, storage, processing speed, whatever, you just flip a couple of switches and they add that and the cloud takes care of it. And then when the Super Bowl comes around for the NFL and their traffic goes off the charts, well, they totally scale it up. It's kind of like, opening the valve on the garden hose, to full, and you can control those things in a cloud environment. I know those are like very simplistic examples. Gen AI models are really kind of huge in their data requirements, right? Just to even get them trained, it's huge. You hear about people, they write all their algorithms and then they start to train them. And sometimes the training, even with high-powered cloud environments, takes months just to, like, they hit start, walk away, and come back in a month, and the model's still training itself. That's like hardcore computing, folks. There's also a lot of concerns about privacy, what data it has access to, and this is one of my big concerns, right? Because human beings very liberally throw their data out there and don't even think about it. And then you throw like an intelligent engine behind it that also has access to your data. And then you got to wonder about the scruples of the people that created the technology. What is their driving force? Are they giving the tool out for free? Why? You think they're not monitoring what you're doing and what questions you're asking? Right? And any online or software tool that's free, there's always a cost, folks. Always a cost. Right? Usually your information is the cost, right? All right, they have some discussion points here, and I just have you can look at these really quickly. I'm not going to go through and answer them, but some interesting questions here. So it says you created I'm looking at the third one, create an application of face detection. Instead of looking for criminals, could it be used to look for political rivals? So like, hey, where's so-and-so going today? Yeah, sure. Yeah. And you know what? It could be used that way. Totally. All right. So you can read those little examples. I do want to put this slide up because I think this one's kind of interesting, because when we look at Gen AI models, they tend to fall into these kind of major categories, right? So we have the chatbots that can have interactive things, right, going on. This one here, I don't know if you guys have ever heard of it, but Tuku, right? This one supposedly has won awards for its realism. I've never tried it personally. We also have all the virtual assistants. So we have like Siri and Alexa and all those kind of tools. Those are powered by Gen AI models, and more so as time progresses. In the old days, it wasn't necessarily much more than intelligent search, but now they're actually putting Gen AI behind those tools, right? And this is kind of what we were talking about with Charles. The bottom two corners where we have image generation and music generation, I think those are pretty interesting. I've experimented with both of those tools, by the way, and they're fascinating and horrifying all at the same time, right? And having been somebody who's done like music in the past, when there's like a tool where you can just give it a couple of prompts and it creates a song, and it's like, even with like singing and vocals and words on it, and it's like, oh my God, you know, I just give up my music lessons now and call it a day, right? But then we have the big one in the middle, which is more about the large language models and the generation of words or code or whatever. And I think we're going to move into this era where a lot of stuff is not generated by humans, because humans are just going to get too lazy to do it. And that kind of both in some ways enthralls me, right? Because if you spend a lot of time creating content, like your whole day is creating content, but then you can just assign it to an AI and it did your work for you and you're still getting paid, great, right? Your day is free and you still have your paycheck. But when are they going to catch on and go, hey, we don't need you humans, right? The robots are in control. Right? All right. All right. So here's the thing. We've gone through this whole project cycle now, and we are just a couple of minutes over, but the whole point of any cycle is that it does repeat, right? So once you deploy something and you get it out there, then you're like, well, how do we make it better next time? Or what new thing are we going to build? And that's where it becomes the cycle, right? So it doesn't end at deployment, as it says. As all good project cycles go, especially the agile ones, they repeat often. The Gen AI models are growing really, really fast, right? But any IT system, typically, you can see shelf lives on like anything from like an operating system to a piece of software or an app or major software release or whatever, however you want to kind of like quantify it all. In IT, typical is something to 3 to 5 years for a cycle. I think with AI, especially if AI has helped to do the generation of the next cycle, which is going to start happening, we're going to see those cycles really shrink down. And what if like a big AI engine can rewrite itself in a month's time? And then the next time around, it can rewrite itself in a week's time, you know, or whatever, right? So you can see this like acceleration that can happen. The other thing where I think it's really fascinating is, when will the AI models, if you think about like object-oriented programming, right, where we create a class and then we can instantiate that class. We can instantiate it as many times as we want. And if you see an AI as a class, who's to say that it can't replicate itself 1,000,000 times to solve a problem, right? Well, it would be limited by the computing power, right? So there's that limitation. But what if it had control over itself? What if it had its own bank account so it could pay the Amazon cloud or the Microsoft cloud to do the, you know, yeah, it goes down a whole deep rabbit hole. And these are some of the things that both enthrall people about AI, because if we can increase the rate of creating solutions to problems, we can solve the problems of humanity much more quickly. Right? Disease, poverty, you know, whatever, energy, whatever, you know, whatever it is. But then we also get worried about this thing we call singularity, which is where the AI becomes self-aware and self-controlled, right? And then are we needed in the picture after that? All right, this actually caps this. You know, there's a little quiz thing here at the end, but that refers to the stuff that we have in the course. So this presentation is over, folks. I'm going to hit the stop button here. So this video is done.